Hello class, so we're going to start talking about the types of forces. You should have, learned some stuff today, but here it is to go in your notes. So the types of forces that we're going to cover are the normal force, the friction force or force of friction, force of gravity, the spring force, force of tension, and last but not least, just talking about, we could call it like the force of a push-pull. For each of these, you should be able to get an equation for most of them and definition. Alright, let's move on. Alright, so I know I wrote normal force first, but we really can't talk much about the normal force until we talk about the force of gravity. Since we've already done kinematics, you've definitely already dealt with gravity. The key thing to this is, gravity is still the same as long as we're on Earth. So you're still going to use, the acceleration from gravity is 9.8 meters per second squared. Alright, you can put a negative sign there if you so wish, or think of it as, hey, it's pointing down, it should be negative. Another thing to think about, what causes the actual force of gravity? Sure, something accelerates, but why is it accelerating? Well, let's think of it a different way. Why is it accelerating has to do with how much mass it is. So we do care about the mass of the object, which should be in kilograms, and will be given by your question. A key point about this is we'll sometimes just call this G because it's such a special number to us. We're going to have to use it so much. So we just write in G for it. So essentially, we know that F equals ma. So gravity is a very simple one as far as, the force of gravity, this is how we write the force of gravity, is equal to the mass of your object times gravity. So just to reiterate, this is mass, and this is your acceleration. In case you guys don't remember what A is in your notes, acceleration due to gravity, which we do know to be 9.8. If you round to 10, that is fine. Alright, so we have to talk about force of gravity to talk about normal force. Alright, so normal force. The definition of normal force is the component perpendicular remember, this means at a 90-degree angle, perpendicular to the surface of contact. So what we mean by that is, so we have, here's a book, here's the table. So we have a book on a table. Your table would be the surface of contact. So the table and perpendicular, our table is flat, so that force would go straight up, equal and opposite to gravity. So your normal force is exactly opposite your gravity in the same direction. So in this sense, your normal force is equal to also mg, and I'm going to say essentially your percentage of mg. This is not really a number we're going to put in, but often it's exactly the same as gravity. This is true. So this is only true for flat surfaces. This will change when we start doing non-flat surfaces. So remember, this is only true for flat surfaces. So I'm about to clear this so we can talk about what happens on non-flat surfaces. So we're still on normal force. However, let's say it's on some inclined plane, like a wedge. We still have a book, which looks a lot like a block on it. So, alright, normal force can only be perpendicular at a right angle to the surface of its plane. This is our surface, here's our right angle. However, gravity is not going to be opposite of it now. Gravity is now going to go downward. We're going to start breaking these into components. You can see, oh look, the amount of gravity going this way, now we can break our gravity into two parts. The part of gravity going this direction is now opposite of it. So you have to break gravity up. So look, if these two forces cancel out, hey, we got this little bit of extra. That is probably going to push our block down. So there's no true equation for normal force. Well, this would be, talk about it later when we get into sine and cosine. But just know that normal force is always perpendicular to the surface, and it's essentially what stops. You can kind of think of it as the force that stops objects from falling through other objects. So the reason your hand doesn't go through the wall unless you punch it really hard, but if you lean on a wall, normal force also works to keep you up from breaking through a wall when you aren't intending to, or even when you are most of the time. Alright, so now we're going to talk about friction. Remember I said, think about friction. What's the two things that make friction? There has to be contact and movement. So there's actually two types of friction. We're mostly going to talk about one, so I'll focus on that one. And that's the force of friction from it being kinetic or already moving. So the force of friction when it's already moving. And so the force of friction depends on two main things, right? Think of, say you have like a smooth whiteboard and say sandpaper, right? Which one's easier to move your hand across of? Hopefully, you can think, oh, well, the whiteboard, because it's smooth. So our material matters. That's what this little coefficient of friction means. That says, hey, the material matters. The other thing is how hard you push, or essentially, or you think of it as how hard is it pushing you back. How hard does the whiteboard push back when you push on it? Which is our normal force. So friction is very related to your normal force. It's just the normal force times whatever your coefficient of friction is. So this is called the coefficient, and this is technically the kinetic coefficient of friction. And this is our normal force. From here, also this little thing, it's another Greek letter. It's called mu. And yes, those who know me, yeah, you could kind of think of it like the Pokemon. The original 151, but it is called mu. I don't know if I spelled that right. You can check me and tell me tomorrow. But it is called mu. So the friction And it depends. Friction's a little different. Like if you've ever pushed something really heavy on the ground, you got to push a little bit harder to get it started, and then once it's moving, it's easier. So the only difference between our force of friction from the kinetics or static means stopped. The only difference from that is that we have a slightly different coefficient, but it is still the coefficient of friction, but it's now the static coefficient. It's a little bit more difficult to get things started moving, and that's because just the friction's a little bit higher when it is not yet moving. And then once you get it to move, that split second after it starts to move, you now use this one. So a lot of them will be like, so a block is already moving. Well, now they say what's the acceleration is going to be. That way most of the time we are going to use this one will be the one we use the most. Alright, other is spring force. So this is the force from, you guessed it, a spring. So think about a spring depends on two things. This would be, you know, what is the spring? And, you know, how far you've pushed it. Right? So a spring does depend on what the spring is like and the displacement you've caused the spring to go. And the more you push it back, the more negative it gets. So this is it's called the spring constant. It's a little different from a coefficient because it does have units. The coefficient does not. So it's newtons per meter. And this, of course, is the displacement, how far it's gone, and this is in meters. So there's really not much more to go into the spring force, right? The more you push it, the harder it pushes back. Alright, and we got tension. Tension is also kind of based on, and it's labeled as Ft, the mass times the acceleration. Often the acceleration is from gravity, right? Because it's a string holding up, equal and opposite to gravity. For example, if you have a box that is hanging from some rope attached to the ceiling. So your free body diagram of this would be your gravity, Fg, would be pulling it down, but since it's not falling, your F tension is equal and opposite to it. And that's really all you really know is like tension comes from strings or cables. For example. Alright, moving on. This will really be the last one. This is talking about just, you know, the idea of pushing and pulling. I just wrote pull twice. So pull and push. So this is just going to be, again, F equals ma. You can write pull or F push. This is where they have to say, oh, well, you pushed it so that it's accelerating this fast, or you pushed it with a force of this much, and the weight weighed this much, how much is it accelerating? An important point to note about all of these is, right, remember forces are directional. Direction does matter. If we go back to your graphs, the x component is the component from side to side. Your y component is this that goes up and down. So when I write, it's the sum of your fx is equal to m times acceleration in the x direction. So this means I am referring just to things that say x, and I realize now that I wrote it in blue instead of red. So your fx is equal to your m times your acceleration in the x direction, and only in the f direction. For talking about your forces in the y direction, it's the same thing. It's only your force that goes up and down times the mass times your acceleration in that direction. Alright, hopefully that was helpful for you, and see you tomorrow.